base. So these includes beams, bridges, arches, window supports, all of the above. So, and we also focus on how we design these structures to make them strong enough to stop them from fracturing, bending, or toppling. Cool. So you want to start with the first one, bridges and tables. Bridges and tables are very similar objects when you look into building them. So a question has always been, how do we build a window into a building? You can't build on top of the glass directly, it'll shatter. There's a bunch of physics into this, and if you load a lot of weight onto it, it'll just break. Like having a hole in the wall introduces a weak point that's otherwise undesirable. So the solution that's used in most cases is a lintel. So it's a wooden plank or any other type of support. They can be made from steel beams, reinforced concrete, or wood. And in effect, you build around where you want the window to be. So the window isn't built directly into the wall at the beginning. You build a wall with bricks, build up on the sides of where you want the window to be, and then once you've reached the correct height, you put a lintel in, and this supports the brickwork above it. So in essence, it's very similar to the concept of a bridge, but instead of supporting people or trucks to cross a river or a different obstacle, it supports the static weight of the wall above it. So for this practical part of this lesson, we'd like you to build a model table. So we have an example here. So we have Valencia. She's in a hurry and needs to build a couple of extra tables for a wedding function at her house. She can't afford to buy conventional tables, but she has a number of wide sheets of wood that she can use for tabletops. So how can you use the sheets of wood to make tables? What kind of designs are possible? So here we've open-ended answer. Any design that you have that's more or less practical is something that we'll accept. A design that doesn't require any fasteners, like the one we've shown here, where it's a flat piece of wood on top to form the surface of the table, and then we have two smaller sections that form triangle-like feet that support it. These are also acceptable, but if you've got different solutions that'll still work, we can go with that. Cool. So Jamia has a plan. She can't describe the plan in detail, but she's given you a rough drawing to see what her work is. So Valencia kind of looks at Jamia's idea, but she doesn't really understand her drawing and how to build this from what she said. So we'd like you to make an improved drawing that more clearly shows what Jamia's tables will look like. You only need to make a quick freehand sketch. So in essence here, we want you to draw this for us three-dimensionally so we can see what's going on. The stick figure drawing above is informative to a degree, but we want you to do a little bit better. So to understand how this table works, build one. An important piece of information to building these correctly. Corrugated cardboard has certain properties. So the corrugations have direction. It's corrugated cardboard. There's two flat pieces of cardboard with this kind of up and down sinusoid shape, these corrugations on the inside, and then they're glued together to make one whole. So the effect is that if you've got a piece of cardboard in front of you and the corrugations are going forward and backwards in front of you, so it means that they have along with the corrugations, they bend easily. But if you go 90 degrees to the corrugations and try and bend it, it's really strong in that direction. So for this one, if you've got this three-dimensional structure here where you more or less have a bend in the cardboard here, make sure that the corrugations are at the right orientation, that it'll bend easily at this point here, but that the table, which needs to support loads coming from the top down, will not bend easily. So if you take this, if you've got the corrugations along the width like we're showing here in figure 8, it'll make a clean bend here. along this direction. But if you do the same with this one, it'll make it, try it yourself, you see it bends weirdly. It doesn't bend in a straight line. It's also very strong in this direction. So if you use this one, figure 9, for the tabletop, it will resist the bending forces if you put something down in the middle pretty well, versus if you do it like this, it'll just bend easily in the middle because the corrugations don't strengthen it in that direction. So build your model. So this is kind of an example. This is a very nice drawing, but we'll accept a rough drawing like this. We kind of just show the design here. So the other thing we want you to look at is make sure that the corrugations are in the right direction. So once you've built this, you need a way to stop these supports from collapsing outwards and downwards so that they just fall flat. You can just use gravity to keep them on, to keep the tabletop onto the supports. There's not a specific way to do that. If you use sticky tape, that's also cool, but you can use sticky tape as well to keep these from expanding outwards, so you brace them. We discussed bracing in the previous lecture video. So copy figure 1. There's a bunch of different ways. The important thing is the support here. So now look at this table that we've built here. Depending on which way the corrugations go, it'll be strong. So if the corrugations go from top to bottom, you can fold it in half lengthwise so that the length and the width is much longer than that. But if you place something in the middle, there's a chance that it'll fold up and over, versus if you've got the corrugations coming in this direction along the width, this object will be pretty weak. So both of them have a weakness, just in different directions. So if you want to improve the strength of the structure, there's a way to do this without having to do strange things. You include 2 pieces of cardboard, but with the corrugations 90 degrees to each other. So that and this is similar to what we discussed in the previous chapter, where you use materials in the direction that they're strongest. And if you've got a material or a member that has weakness in a certain direction or a certain situation, you combine the properties of different members and different materials so that overall the one that's always strongest is taking the most of the load. So this is what you can do here. You've got 2 options. You can take a second one on top with the corrugations in a different direction. And if you bond them together with a little bit of glue or something, you'll have a pretty strong table. Because if it wants to fold in one direction, the other piece of cardboard that it's been bonded to will have the corrugations at 90 degrees in a different direction. It'll be strong to both. The other one is reinforce it at the bottom. So the addition here is you just added a separate reinforcement at the bottom and it'll make it strong. The disadvantage here is that if you want to sit at this table or use the space under it, you can't. It's full of supports. So depending on how you want to use the table, there are 2 options here. So supporting the table in the middle is a very legitimate solution. It also, in some cases, will use a little less material, so they're both good. So we want to continue this discussion. Now that we've shown how to support, a flat structure that you use to access something or bear weight. So you've got this flat sheet, and this is very similar to a bridge. So there's a number of different types of bridges. The beam and column bridge. So these work similarly to that example where we strengthened the table by having those corrugations at 90 degrees. So you've got these slabs or strong reinforced concrete on top of columns, and they bear their own weight and they transfer it to the bottom here, but they don't have reinforcements out from outside. It's a load bearing beam, and these beams transfer weight to columns. The second option is the arch bridge. So this is quite an interesting design. It uses this arch. So when you apply pressure to this arch, at no point in this kind of design is there any tension. So this column is in constant compression and it pushes, and as soon as you apply any weight, the columns between the beam and the arch transfer all of this force to the arch, and the arch is incredibly strong in compression. And its design means that it will always be in compression. If you try and push down from here, it'll try and push the sides of this into the mountain or into the supports, and in that direction it's always super strong in tension. If you were to pull on this structure, it would be a lot less strong, but bridges don't really pull. Gravity points down, so the natural weight of the bridge and the weight of the arch strengthen the structure. So a very nice design. The third option we have here is the truss bridge. Truss bridges use the principle of triangulation that we spoke of earlier to strengthen a bridge like this. Sorry for that. So each of these, like the truss here and each of its members, are built into triangle-like shapes. They use the strength of the material under tension or compression to build a whole bridge. This is also usually a well-designed bridge. They're not suitable for all sizes and types of bridges and all weights, but they can also be built relatively easier, but they're not used for the largest of bridges. Suspension bridges work a bit differently. So they still have a column, they still have a beam going across that's supported, and it's suspended using steel cables that are supported by columns in the middle. They're usually also designed so that the net weight of the bridge and people crossing doesn't try and pull these columns over. They're also supported by very, very strong foundations and anchored at both points. So this is a massive, massive steel cable, incredibly strong, incredibly thick, with multiple smaller steel cables bound together, like they're woven together like a rope, and then it's got smaller supports hanging off and supporting the bridge, while most of the weight is borne by these columns, and they're also anchored at both points to increase their strength. If there's a heavy load in the middle and the loads are transferred into this main suspension, this main cable, and it tries to pull on here, that will be countered by the support on this side. So there's also a very strong bridge. A lot of the very large bridges work on this principle. Cantilevered bridge works similarly. It works on a different principle, although similarly. So the cantilevered bridge uses a balance of forces on a similar kind of column support to keep the structure strong. It's to some degree a truss bridge on a bunch of columns. Also a very strong design. Depending on the weight and load, it can be very viable for a lot of situations. Okay, investigate bridges. So look at the figure we've drawn here. We want to build the bridge across this length from A to B. So there's a river or something in the way. We need to cross this distance. It's 30 meters. So yeah, draw a quick sketch of this gap that we need to cross. Now that you've drawn this area that we need to cross, draw an example of a type of bridge that you would be able to use to cross this distance. Any feasible design from the previous ones we've listed that you can draw out in a way that makes sense is good here. So yeah, we've got specific questions here. So now that you've drawn a sketch, draw a bridge across it and answer the following questions. In what way will the bridge be supported so that it doesn't bend when a heavy truck is loaded over it? If you just put a straight beam on here, a beam across point A and B, and you drive a truck over it, it will start bending in the middle. How are you going to support this bridge to prevent that? Are you going to have support structures underneath? Are you going to have a column that passes through the top and suspends the bridge? What are your options here? So for this kind of length of bridge, what kind of materials would be suitable to build this out of? So a lot of straight concrete that hasn't been reinforced, and a lot of other materials are not very strong in this kind of bending, and in these bending moments that will happen when a truck drives across. You've got a very heavy weight in the middle. How are you going to support this? The question is, how wide should this bridge be? So we've given you the length of the bridge, what area it needs to cross, but how wide does this bridge need to be? So you see car traffic here, so think about that when you answer this. And the other one is, how many cars can be on the bridge at the same time? So this will depend on your answer in the previous question. If you've decided that it needs to be a bridge for a 2-lane road, you've got 2 cars that can pass by each other at the same time, it'll have to carry at least 2 cars. If you've decided to do a single lane bridge where only 1 car can pass at a time, it has to be able to pass at least 1 car. Just make sure your answers match up there and that you thought the whole process through about what kind of bridge this is and what your design looks like. So yeah, another nice example, you can do this in class. We strongly prefer it if you do this right now, is to build a suspension bridge. Yeah, so we'd like you to focus on building a suspension bridge. So this is pretty simple. Use the diagram here in figure 20 as your guide. You can do this between 2 tables with pieces of cardboard and sticky tape. So you need to anchor your bridge to both tables or both surfaces. You can do this between 2 chairs. World's your oyster. You just need 2 surfaces, like a suitable distance apart, probably not more than a ruler or 2, like 30 centimeters, 50 centimeters, and then span enough sticky tape between them to build the bases of this. Then once you've got that between there, you need to give yourself something to walk on. So you can use pieces of cardboard with the corrugations in the right direction to create a surface that you could walk on, and then make sure that that sticks to the tape well. And then wow, you've got a suspension bridge. It's held together by tension and anchoring points at both parts. So these anchoring points are what take all of the weight and the force. This reinforces it, and voila, you've got a bridge. So yeah, there's a couple of variations on this. In a cable-stayed bridge, a suspension bridge just kind of needs the top and the bottom. You need something to hold your hands onto, and you need a base to walk on. But there are a number of variations on how you support this. So for one, you just embed supports directly into the ground, or attach it to a large boulder on the other side. Suspend these lines across, build on top. Make sure you've got a handrail with these cables for you to walk on. Then you've got a bridge, but you can also suspend different parts of it onto poles that are sunk into the ground, so that they can use the rock or the foundation on each side to support themselves. So yeah. So this here is a second type of bridge that works on a similar principle. It's a cable-stayed bridge. So to build a model of this, take a piece of cardboard, run 3 lengths of string across it, and use sticky tape to affix these to the underside of it. Then flip it around and pull the strings up to a central point in the top here, like figure 21. So now you've gotten on a cable-stayed bridge. There's a single support that holds up this bridge, and you can go across it, and these cables here do the supporting of the bridge. So yeah, making sure that structures are strong enough. So yeah, here's an example so we can discuss what we mean by strength and how we apply the right materials and right concepts to when we build or use these kind of structures. So here I've got a table with a glass top. Some of you have seen a coffee table like this, and I decide to put a very heavy pot on top. Like if you put a poiky pot on top like this and nothing on the glass surface, the odds are there the glass is going to crack or break. Your structure is going to fail. This pot's going to fall on the ground. You don't have a table anymore. So it's not the best design of that. So when you design these kinds of supported structures, you need to make sure that they're made of the right material for the right job and that all of the different parts can work. There's also this possibility that depending, if this is very strong reinforced bulletproof glass, there's a chance that this won't break, but if you put a very heavy pot on this and you've got flimsy supports, thin pieces of pallet wood or something similar, there's a solid chance that they could break and the structure can fail that way, which also will result on a large pot of food being spilled on the ground and you not having a useful table anymore. So if you look at this in your class and your surroundings, look at the desk that you're working on. What is the material that the top of the desk is made of? What is the... Let me with my voice illustrate the one that I'm working on. I'm working on a fully wooden desk. The top slab on top, this beam is completely made out of thick wood. Let me measure this. It is around 2.5 centimeters thick pine wood, and this can support a lot of weight. A solid piece of pine wood bound together can support a fairly amount. So this is a fairly thick, beefy slab at the top. The supports are equally thick two equally thick boards of pine wood going down. So mine doesn't have 2 legs, doesn't have 4 legs like some other tables might have. It has 2 very, very wide legs on the table on the sides. And these wide legs at the bottom are fixed to a shorter length of equally thick pine wood so that the base that it's being supported on is much wider than just the legs. So it's kind of got these legs coming out at the top and it's got these legs going down and these wide feet coming at the top. And the feet are about as wide as long on each side as the top of the table is. So yeah, this is a fairly stable desk. It doesn't twist or do anything easily. So if I wanted to make a table, would I decide to swap out the 2 large legs of this table for 2 thick pieces of rubber? Or to use rubber pipes to make a 4-legged table? Probably not. There are better ways to do this. Rubber doesn't have any resistance to bending. So if you were to make a table out of this, it would just flop down immediately. Versus if you make it out of the table that I have here with me, very thick wood, it's a lot easier. It's a lot stronger, table's not going to fall down. So yeah, there's a second one. Let's look at figure 23 and we can see here a separate mechanism for a table to not be well designed or to be very fragile or not to be stable as well. So we here have a round top of the table made out of wood presumably or cardboard, and then we've got 3 bottles with their ends at the bottom. So we've got the thick part of the bottle at the top supporting this cardboard disc, and we've got these at the bottom supporting the structure. Is this the best that you can do? Remember, this cardboard disc is not glued to these 3 legs at all. They're standing free. This means that you've got only the small area at the bottom of each bottle supporting it, all of this weight on the top, and nothing gluing them together. These aren't bound in any way, they're just standing there. Why wouldn't you do this? What's going to happen if you bump one of these bottles lightly? This bottle is going to fall over, the whole table is going to collapse. If I wanted to improve this table here, this little impromptu table to keep some stuff up, you would flip the bottles around so that the thick base at the bottom that's got a wide area to support itself is keeping this bottle balanced and stopping it from falling over, and then the tops there that are a bit smaller can at 3 different points can support the round piece of cardboard at the top. This will be a much better table. Although for like bonus points, don't use glass bottles. Glass bottles have the additional thing that you place any weight on them, glass cracks easily and then it becomes dangerous. If you were to use plastic bottles for this, bonus points. So each of these 3 images here shows different ways that bridges can fail. describe to me what's going to happen in each of these and what's wrong. So from this first figure, we've got a very heavy car going over what is essentially just a beam that's being used as a bridge. It doesn't have any reinforcements in the middle or cables from the top suspending it. So what's most likely to happen here? This heavy car is going to drive across, it's going to snap in the middle, your car's going to get stuck in the river and you can't get out because the bridge is now broken. If you wanted to prevent this with this type of bridge, you could support it at the bottom. You could have a type of suspension bridge. We have a support at the top that stops this from collapsing. Here's a different problem. Here we have a bridge that's not flexible, it's made of support beams with supports at the bottom. Here starting to crack in the middle, and now it becomes impossible. How would you stop this kind of problem? So in this case, it may be that this bridge does have supports on the side, but the beam material is not made of the right. The beam is not made of the right material. This could be plain concrete, and if you wanted to create a beam that can resist breaking like this in the middle, it would be better to use reinforced concrete or steel. Here's a different problem that I think if you've played with a seesaw, you can kind of see this happening. This bridge, if you stand on one end, on the other side of the support, the other side of the bridge lifts up and can fall over or start twisting and then move off. So how would you support this problem? How would you solve this? So think about that for a minute. Pause the video if you want to. So for this type of bridge, your problem is that when you start applying a force in this direction, this beam here acts as a lever, and you start applying force here, it gets amplified with distance, and then it moves up on this side. So you would need to be able to counteract the force applied here by stopping this beam here from moving up. So your options would be to weigh it down at each end, or to affix it in some way, nails, weighing it down, tying it down to this log to make sure that it can resist being moved up or down. So yeah, look at this large one here. So these are two different types of bridges. Oh, I don't. Alright, so if we look at question 6 here, we can see that they've given us a diagram of a small table here in figure 27. So we'd like you to show us and to discuss in which ways this table could fail. So look at the design, look how high it is versus how wide it is. So yeah, so if you look at it's a very tall table and the supports are relatively close to each other, so it could be easy to topple over. So think of these type of questions. Think what would happen with these relatively thin legs on the table if you were to put a heavy load on it. So on question 7, we have pictures on the next page of a suspension bridge and an arch bridge. So in a suspension bridge, the deck of the bridge hangs from the cables that carry the load. Explain in what way an arch bridge is different from a suspension bridge. So look at the two diagrams here in figure 28 and figure 29. We have here a good example of a suspension bridge. It's got its columns here that help to support the weight of the cable and the bridge. We have the cables here with the anchoring at each side, and here we have a nice image of what an arch bridge looks like. So it's got the central arch that's held in place at each end with foundations, and this arch supports the weight of the bridge. So we can see here, so let's compare them. So for this bridge here, With the cables are under constant tension and they take the weight of the bridge, and then the support is given by the columns and by the anchoring. But all of these parts that provide support are under tension. The main cables are under tension, and these going down to the bridge are also under tension. The bridge hangs on these cables to some extent. Versus here, if you look at this arch bridge, the arch here carries the weight of the load, and this arch is under compression the whole time. So the arch is under the bridge as opposed to supporting it from above. The arch is under compression, and the arch has all of the weight and its own weight supported by these supports at the end versus by columns here. So yeah, your homework that we'd like you to do and to explain. So work on the following. Where are lintels used in houses and what are their purposes? So we've spoken about this earlier in this lecture. So can arches be used instead of lintels when houses are designed and built? So make a freehand sketch to illustrate your answer. So we've spoken earlier about the types of supports that you can get for windows. So if you were to try and design a window with an arch instead of a lintel, is this possible? Think about it. It's mentioned earlier here as well. What is the difference between a beam and column bridge and an arch bridge? Think about the types of support, if they're supported from above or under, how the bridge looks. And number 4, when you use an arch bridge instead of a beam and column bridge, think about the type of terrain that you will be able to use this in. An arch bridge can be used effectively to span a very different type of gap than you can use a beam and column bridge for. Think of where you would be able to build these and where the needs of these two bridges are met. An arch bridge needs strong supports at either side, and a beam and column bridge needs to have a place for the columns to go down and be anchored into. So think about that. So yeah, this is the end of this lecture. Thank you so much.